Good morning, everyone. Good morning. Hope all is well. Hope everyone's doing all right. All right. Any general questions, concerns, comments before we get rolling? Everybody doing good? Straight. All right. So, all right, did 3-3 last class. Looking at 3-4. Let me check out something real quick. All right, so looking at 3.4 today, zeros of polynomial functions. So don't forget zeros. We talked about this last class, zeros, roots, and solutions all mean the same thing. So when we look at that first topic in this section, the rational zero theorem, it really could be called a rational solution theorem. Basically, it's giving you the list of all possible rational zeros. All right, so to find a list of all possible rational zeros, we take the fact is, first of all, we recognize it's plus and minus. So it can be plus or minus for each number that you get, but you take the factors of your constant and place it over the factors of your leading coefficient. All right. So where this comes from is if I had 2x plus 3 equal to 0. The 2x is my leading coefficient. That's the number that's sitting in front of my variable with the highest exponent. That's your leading coefficient. And then my constant is the number that is not associated with the variable at all. So 2 would be my leading coefficient in this example, and my constant would be my 3. Now, when I solve this, I will subtract 3 from both sides and then divide by 2. And notice the position of my solution. I have my constant over my leading coefficient. So that's where this possible list of rational zeros come from. That's why you have your factors of your constant over the factors of your leading coefficient. Now, this is my actual solution, but this is something that you do when you don't have a clue as to what your solutions would be and you need a place to start. So this gives you a list of possible solutions, but it comes from this idea, having your constant over your leading coefficient. All right, I'll scroll up. All right, so this next one, the first one under this type of thought process, it says list all possible rational zeros of f of x equal to 15x cubed plus 14x squared minus 3x minus 2. All right, so our constant is 2, and our leading coefficient is 15. My factors of 2, 1 times 2. Factors of 15, 1, 15, 3, and 5. Is everybody okay so far? Our constant is 2. Leading coefficient is 15. Factors of 2 is 1 times 2. Factors of 15, 1 times 15, 3 times 5. So now we're going to take each one of these and place it over each one of the 15 factors. And so that's what we did right here. 1 over 1, 1 over 15, 1 over 3, 1 over 5, then 2 over 1, 2 over 15, 2 over 3, and 2 over 5. Everybody good up to this point?
I have a question.
Mm-hmm.
So how do you know that the loading coefficient is always going to be the first number? Like, why wouldn't it be 14 or 3?
Well, it's not necessarily going to always be the first number. It's always the one associated with the highest exponent of your variable.
Okay.
So if I put that 15x cubed in the back, 15 still is going to be my leading coefficient because it's assigned to the x cubed.
Gotcha. Okay. Thank you.
Yep, no problem. And just to make sure everybody's with us, let's say if we had x to the 4th in front, then 1 would be my leading coefficient now because 1 is in front of x to the 4th. So
how did you get 1 over 1?
You took this one and placed it over this one.
Okay.
And then you take, that 1 and place it over 15. Then you take the 1 and place it over 3. Then you take the 1 and place it over 5.
Okay, thank you.
Mm-hmm. Everybody good? And then you do the same thing with 2, just making sure everybody's okay with the process. So you take each one of these, place it over each one of these, and then do the same thing with, do that with 1 and then do that with 2. All right, and then you reduce as much as possible. Make sure you don't have any repeated values. So 1 over 1 is just 1, like 2 over 1 is just 2. And so let's see what I wrote here. Yeah, 16 possible rational zeros. Because that plus or minus goes, I just shorthanded it, but the plus or minus go in front of each one of those terms. So it could be plus or minus 1, it could be plus or minus 1 over 15, plus or minus 1 over 3, and so on. All right, make sure we're okay before we do it again. Just want to make sure we're okay with this list.
Are we expected to plug these in to see if they're actually valid?
Well, when it comes to actually finding the solution, and we're going to, let's say if they said find the solutions of this equation, then what you would do is plug +1 in and see if you get 0. And you can do that with you can check that with your calculator. Going back to our remainder theorem test that we did last class, plug 1 in. If you get 0, then it's a solution, and then you can go from there. If not, then plug in -1 and stuff like that. So this gives you a place to start. But yeah, it doesn't actually give you what an actual solution is. So yes, that's how you would determine whether you have a solution or not. So most definitely, and that's a good question, most definitely all of these are not solutions. And it's possible that only one of them would be a solution, and you would just plug it into the calculator. Because I wouldn't suggest do that by hand because you got 16 times that you have to calculate that. I would suggest plugging it into the calculator and just switch out the numbers and see if you get 0.
Okay, thank you.
Mm-hmm. All right, questions before we do the next one. Same thing, but just give me another example of doing so. All right. So here we have 4x to the 5th plus 12x to the 4th minus x minus 6. This time our constant is 6 and our leading coefficient is 4. All right. 6 is 1 times 6 and 2 times 3. 4 is 1 times 4 and 2 times 2. So we're going to take each one of the constant, each one of the factors from 6 and place it over each one of the factors of 4. So this is going to be a little longer. Yeah, it's a little longer. All right, let me erase these. So 1 over 1, 1 over 4, 1 over 2. And since 2 is repeated right here, we don't have to write it twice. So really it's only 3 numbers, that we're actually using from 4. So, and then that's 6 over 1, 6 over 4, 6 over 2, 2 over 1, 2 over 4, 2 over 2, and then 3 over 1, 3 over 4, 3 over 2.
I'm kind of confused on how you get all the fractions.
Mhm. So you take each one of these and place it over each one of these.
Oh, I gotcha. Okay.
Okay, that's good. Okay.
Yes.
All right. So yep, just re-emphasizing what she just asked about. You always take each one of your constants and place it over each one of your leading coefficients. All right. Once you have your list, then you simplify your list. Cross out any ones that are repeated values. So 1 over 1 is just 1, 1 over 4, 1 over 2, 6 over 1 is 6. Now 6 over 4 reduces to 3 over 2. 6 over 2 reduces to 3. 2 over 1 is 2. 2 over 4 is 1/2. So we don't have to rewrite that. 2 over 2 is 1. Don't have to rewrite that. 3 over 1, we already have that. We don't have 3 over 4, so it's right here. And we already have 3 over 2. So this will be our list. And once again, we have 16 possibles. All right, are we good? Everybody okay? All right, so here, let me see if I did, hold on 1 second. All right, so here, find all zeros. So let's look at one of your classmates did suggest of how we would determine what we have zeros, whether we have zeros or not. So finding all zeros, we have x cubed plus 7x squared plus 11x minus 3. So notice that we're going to have 3 solutions here. Highest exponent of x is 3, so that gives us a hint to having 3 solutions. Our constant is 3. Leading coefficient is 1. Factors of 3, 1 times 3. Factors of 1, 1 times 1. So we're not going to have that many in our list. Everybody okay so far? And I meant to put this here, normally I say it. All right, so our possible zeros, you take 1 and 3 and place it over 1. You know, it's the only options that we have over here is just 1. So that'll be 1 over 1 and 3 over 1. And that's only 4 possible solutions. So we have a short list here. Oh, okay, I did write it right there. Okay. I thought I wrote it somewhere so I could erase this. All right, so there's 4 possible solutions. So we're gonna use synthetic division to see which is a solution. Or just like I mentioned to your classmate, and I wrote it over here in the blue, so I'm gonna scroll up in a second. Or you can just plug them into the function to see which one will be a solution. Remember, when you plug it into the function, that's your remainder theorem. If it comes out to give you 0, then that means it is a solution. I'm going to, so I'm pretty sure you guys know how to plug values into an equation. I'm gonna just run through synthetic division a couple of times, make sure, we get a little practice in doing the synthetic division. So that's why I did that down here. Is everybody okay? Notice our 4 options. 1, -1, 3, -3. Let's see the final 0. All right. So looking at the first one. If I did 1 as a solution, remember our coefficients are 1, 7, 11, and -3. So that's where these values came from. So you bring down 1. First step, 1 times 1 is 1. 7 plus 1 is 8. 1 times 8 is 8. 11 plus 8 is 19. And then 1 times 19 is 19. Add those together, you get 16. So it's not a solution. If I were to plug it into the equation, I would have gotten 16 as well. So remember, this is what you will get whether you plug into the equation or you do synthetic division. But we need 0 in order for it to actually be a solution. All right. Questions before we go to the next one? All right, doing -1. Same process, same numbers up here, except now we have -1 instead of +1 because we're going through our list. So we know 1 didn't work. So now we're checking out -1. So bring down 1. -1 times 1 is -1. Add them together and we get 6. -1 times 6 is -6. Add them together, we get 5. -1 times 5 is -5. Add -5 and -3 together, we get -8. Once again, we don't get 0, so it's not one of our solutions. Also wanted to reemphasize the process of you could plug this into your equation, see what you get. You should get -8. I'm just running through the synthetic division process because, just make sure we have practice on doing the synthetic division. At this point, feel like you guys should be pros at plugging in values. So, but when you plug it in, you should get that -8.
I have a question.
Yep.
So when we started, you said because the highest exponent was 3, we should have 3 solutions, but we've already eliminated 2 of 4.
Mm-hmm.
So how does that work?
Chinese fiddle for you. No, just play. What's going to happen is it's possible to have imaginary numbers. See, this covers your list of rational zeros, but it is possible to have imaginary solutions.
Okay, thanks.
Yep. That's a great question. I didn't know, I was wondering if anybody's going to catch it, but yeah, so it is possible. And you guys wouldn't get anything this, extensive, but it's possible to have, let's say, 20 possible solutions and only one of them actually, let's say 19 possible solutions, not 20, and only one of them actually be a real solution. And let's say that's the last one, but that's where you do research and all that stuff like that. You could go through all of them and the last one actually be a solution, and then any other ones would be imaginary. So yeah, that's how that could work. Yep. All right. And see, like in this case, our solution ended up being the last one. So we tried 3, we ended up coming out and give 120, but -3 ended up being a solution. And I didn't mention the other part of it. It could either be imaginary or it could be irrational. So it can be real, but it just wouldn't be a solid number like 3 or 1/3 or something like that. So, yep. So it could be irrational as well. Still be real, but irrational. Like when we use the quadratic equation, we can come out with something. Notice that'll be a plus or minus, so that'll be 2 values right there. So let's see what I got over here. Yeah. So we see -3 once again is our solution through this process. So like your classmate mentioned, though, we're gonna have to figure out what the other 2 are. Just give you a chance to copy. See what's over here on the blue. Oh, already. Somebody must have asked that again. We already talked about that. All right, so what this does for us, once we find out that we have a solution, we do still need to, let's say if you went through plugging in all your values. So you plug in your values and you find out that this is a solution, then you would have to do synthetic division to break down your equation to get this. All right, so at some point you will need to do synthetic division or divide it, long division. Either way, you're gonna have to do division, to break down your function to get it to this. And so we have one of our solutions is -3, and now we have this left over x² plus 4x minus 1, and we want to be able to solve it now. So we cannot factor it. If we could factor it, then we would still have solutions left, a part of our list. That would be a part of our list. We cannot factor it, but we will use the quadratic formula to go ahead and solve. Right down with synthetic division. So using the quadratic formula, A is 1, B is 4, C is -1. All right, you're okay with the substitution, 4n for B, 1n for A, Cn, or -1n for C. So under my radical, that's 4², and that negative times 4 give you a positive, because we have -4, -4, and then -1 times that. So then that'd be 16 plus 4 under the radical, which would be 20. Square root of 20. We can break up this way. Break it up into 4 times 5, then take the square root of 4. That'll give you 2. Of course, if I scroll up too far, let me know. Then you have -4 plus or minus 2 square root of 5 over 2. Take that 2 up into each one of your numerators. 2 can divide into 4, and 2 can divide into 2. And that'll leave you with -2 plus or minus square root of 5. So here we didn't have imaginary, but we had 2 irrational solutions. And so that's -2 plus square root of 5, -2 minus square root of 5, and -3 are our 3 solutions. Questions? Any questions? All right, can I scroll up? Everybody good? All right, so the complex conjugate theorem. Another possible solutions. We have if a plus bi is a solution of f of x, then a minus bi is also a solution. So we talk about your complex conjugates. The only thing that's different between the conjugates is the middle sign. So if I have 4 plus 5i, the conjugate is going to be 4 minus 5i. If I have -2 plus 7i, then -2 minus 7i. And then and the middle numbers, all the middle sign always affects your imaginary part. So basically we're saying that the imaginary part will have a different sign. So when you look at, if I have -8i, the complex conjugate would be +8i. So it's always your sign for your imaginary part will be different. That would be your complex conjugate. And if you have one, then you automatically know that you have the other. All right, scroll up, okay. All right, so first example under this type of thought process, let's find a 4th degree polynomial function with real coefficients that has -2, 2, and I as zeros, such that f of 3 is equal to -150. Give you a chance to write that down. So they want us to find an equation that fits these characteristics. You know, in the past, we've had equations and they want us to find the solutions, or we have functions, and they want us to find the solutions. This time we have the solutions and they want us to find the function. So first thing we start off with is we recognize that it's a 4th degree polynomial. So that means we should have 4 solutions that's going to help us to get to that 4th degree. 4th degree is just the highest exponent is 4. All right. They give us 3 solutions. And then they say when I plug in, or when we plug in 3, we should get out negative 150. So those are the things that we have that are given, things that we have at our disposal. And green are just stating what I said verbally. They give the solutions and want to know what function produce. They should say produces. Thanks. What function? Can I scroll up? Hold on to the black. Now, so they gave us 3 solutions, but they expect you to know that you have 4 actually. So x is -2, x is 2, x is I as far as our solution options. And also x is -I, and that goes back to the complex conjugate theorem. So whenever they give you an imaginary number as one of your solutions, they assume you know the complex conjugate is another one of those solutions. So if you ever see anything I, they assume you know that 2 solutions are included as a part of that set. Any problems? All right, so now we're going to reverse engineer, some sort of reverse engineer, reverse the solving process. So if I have x equal to -2 as a solution, that means I had to have x plus 2 equal to 0. You know, it's one of my factors. X plus 2 is one of my factors because you want -2 from both sides in order to get that x equal to -2. So I'm going to rewrite my function by using x minus whatever my solution is. So whatever your solution is, you're going to do it that way. So let me erase some of the stuff. Got a lot of stuff going on here. So right here is the rewriting of our function. So you're always going to do x minus whatever the solution is. And then we'll simplify that in a second. All right. So also notice that we don't know at this point if anything is going to go in front of our function. So we put an a there. We don't want to put an x because that would confuse us with all the other x's going on. So we put an a there. That's where that last initial condition will come into play. And you'll see that when we get there. But you put an a in front of all of this just in case there's a number that will go in front to help us to adhere to the conditions that we have. So now here, all we did was simplify the expression. So negative to negative turns positive if you have it. So that'll be x plus 2, x minus 2, x minus 1, and x minus I, and x plus I. All right, everybody okay? So now, whenever you have your imaginary or your complex conjugate, it's best to go ahead and multiply those together. And since we have this here, we'll multiply these together. We call it. All right. So you go ahead and do your binomial distribution. And the same thing here. And we get this result. So x times x is x squared, x times -2 is -2x, 2 times x, 2x, 2 times -2 is -4. Then the other distribution, x times x is x squared, x times I is ix, negative I times x is negative ix, and then negative I times I is negative I squared. So in both, middle terms are going to cancel. All right, and then don't forget I squared simplifies to -1. So that goes back to when we're using our complex numbers. So we have x squared minus 4, x squared minus -1. Of course, negative to negative is positive. So we have x squared plus 1. And we can FOIL that out as well. So FOILing that out, that'll be x to the 4th plus x squared minus 4x squared minus 4. Combine your like terms, that'll give us -3x squared in the middle. So we're not finished yet, almost finished, but we have an a that we have to give an account for to see if it's going to be a number other than 1. All right, click OK. So the last condition, the last initial condition that we had was f of 3 is equal to -150. So that means when you plug 3 into your function, you should get out -150. All right. So that's what we're going to do. Plug in 3 and set it equal to -150 and solve for A. So that A is going to solidify us getting -150 when we plug in that 3. So we plug it in here. So that's 3 to the 4th minus 3 squared, 3 times 3 squared minus 4. So it'd be 81. 3 times 9 is 27. So 81 minus 27 minus 4 is going to be 50. All right, done with the purple. All right. So that's 50A equal to negative 150. Divided by 50, A is equal to negative 3. Any problems? So to finish off the problem, you go ahead and plug in negative 3 in for A. Distribute, and that is our function. That's our answer. Took a few steps, but we got there, right? Questions? Any questions? All right, let's do another one just to make sure we're okay. Same type of problem as previous. I just wrote the details in bullet form instead of writing the whole thing out. So this time we have a third degree polynomial. They give us the solutions of negative 5 and 4 plus 3i. And when you plug in 2, you get out 91. All right, so third degree, we should be looking at 3 solutions. They give us 2, but one of them is imaginary. So they gave us 4 plus 3i. That means 4 minus 3i is going to be the third solution. So don't forget the way we reverse the process of solving or reverse the process of getting this function. We want to recognize that x equal to negative 5 was first. X plus 5, so the way we write that is x minus negative 5. Wrote that a little bit over here. All right, so that's what we did here, and make sure you hold true to that when it comes to your imaginary or your complex numbers. So it's x minus negative 5 here, x minus, so you have to put parentheses over the 4 plus 3 because it need to be, that minus needs to be applied to each one of those terms. And the same thing here, x minus 4 minus 3i. That's always a process, put x minus whatever your solution is. That covers yourself. All right. So go ahead and simplify that. You have negative to a negative turns positive. Probably use red. Negative to a negative turns positive. And this minus sign goes to each term here. This minus sign goes to each term here. So it'll be x plus 5, x minus 4 minus 3i, x minus 4 plus 3i. Then we would distribute each one of these numbers or each one of these terms into each one of those in that parenthesis, the next parenthesis. So just like before, the imaginary, the one that involves have what the parentheses that have the complex conjugates, those will be the ones we go ahead and multiply because they're going to be some things that cancel out for us. So I'm not going to mess with this x plus 5 yet. Now you could if you want, but to me the best practice is to just go ahead and use the complex conjugates because they will have things that will cancel out for us. So let me erase this first. All right, so when you FOIL that out or do your binomial, your trinomial distribution, that's going to be x times x, which is x squared. And that x times negative 4 is negative 4x, x times 3i, it's going to be 3xi. Then distribute the negative 4. Negative 4 times x is negative 4x. Negative 4 times negative 4 is positive 16. Negative 4 times 3i is negative 12i. Then distribute the negative 3i. Negative 3i times x, negative 3xi. Negative 3i times negative 4 is negative 12i. Or positive 12i because negative times negative. And then negative 3i times 3i is negative 9i squared. Questions or problems with our distribution? So whenever you multiply your conjugates or the expressions with the conjugates in it, all of your terms with i's should cancel out. So we have 3xi and negative 3xi. We have negative 12i and positive 12i. Probably go orange on that. All right. So we also can combine alike terms. We see negative 4x and negative 4x will give me, oh, let's get my original. Will give me negative 8x. And then I squared. Once again, I squared simplifies to negative 1. So we can finish simplifying this expression. We have this 16 and negative 9 times negative 1 is positive 9. So 16 plus 9 will give me 25. And now we can go ahead and finish this distribution by distributing each one of these. All right. That gives us x cubed minus 8x squared plus 25x plus 5x squared minus 40x plus 125. Any problems? Any problems? Combine your like terms. Negative 8x squared gives you 5x squared. 25x minus 40x gives you negative 15x. Almost finished. Almost finished. We still need to figure out what A is going to be. Let's scroll up. All right, so our last initial condition was f of 2 is equal to 91. So when I plug in 2, I get out 91. That's what I did. Took this and plugged 2 into it. So that's 2 cubed minus 3, 2 squared minus 15, 2 plus 1, 25. And, we need to figure out what A is going to be for us. And we're going to set it equal to 91. Two cubed is 8. Then 2 squared is 4. 50 times 2 is 3. 3 times 4 gives that. I said 15 times 2 is 3. 15 times 2 is 30. 3 times 4 is 12. Eight minus 12 minus 30 plus 125 is 91. So that's 91A divided by 91. A is equal to 1. All right. All right, so plug in 1 for A. That doesn't change anything because it's just 1. So our answer is x cubed minus 3x squared minus 15x plus 125. Any questions? Very good. Everybody straight. I believe that is it. Yeah, that was me. There's some stuff somebody asked about. So that's it for this section. Any questions, concerns, or comments before we close? Very good. Everybody straight. All right. Well, you guys have a good day, good weekend as well. Be safe, and I will see you on Monday.
Thank you. You too.
Thanks. Take care.
Thank you, Mr. Tucker.
Take care. Have a good one.
You have a good one.
Thanks. You do the same.